Okay, so homework 2 and project part 1 are out. So don't forget, meetings start this week. You should all have your teams. If you were put on a random team, you got an email from me saying what your team is. If you didn't get an email from me and you did submit the the team formation form, that means everything went great and you have your team. If you do want confirmation, if you're just not 100% sure that the team was formed properly, you can always send me an email. I'll just be like, yep, I got it. But everything should be fine. You shouldn't have gotten an email unless you were put on a random team. So since we all have our teams, project part 1's released, so you can start figuring out what to talk about. Meetings start this week, so please fill out your meeting report forms for each meeting. So this week, at the end of the week, I should have a submission from everybody. Make sure you don't forget to fill those out. And those of you not paying attention to me saying this right now, I'm not going to feel bad when you forget to fill out the forms and I take away some AOs on the project submission. That's just the way it works. Sometimes it's never the students who pay attention to who forget to submit that form. It's so easy, just submit the form, but if you're not paying attention to anything, it's hard to know to submit the form. Okay, let's get started on some content. Any questions before we get into it? Okay, what is authentication? So this is where we're starting to build some extra functionality to our apps. We're taking our apps to the next level here. So far, everything we've done, for the most part, was just sending the same content to every single user, regardless of anything else. The only small exception is the visit counting cookie they built in LO2 of homework 1. That was the one exception to serving everybody the same exact content. We had one integer in the form that was a little bit different. Other than that, we're treating every request as exactly the same no matter who sent it. We want to change that. That's not how we use the internet these days. You expect to log into an account and be treated as you're navigating the site. For our purposes, when you're sending chat messages, I want that chat message to be associated with my account so people know that I said that, not just that somebody said it. And homework 1, everybody's just guessed, and it's hard to know who you're talking to. If there's 5 people, who the hell's saying what? We want to change that. This happens in 2 steps, registration and authentication. And we're not actually getting full login today. It takes a few lectures to really talk about all this. We're not going to get into full login until Wednesday when we talk about auth tokens. Today we're just going to talk about authentication, which is a user registers. They create an account. They're going to register their username and password, for our purposes on the homework anyway, just username and password. And then when they want to authenticate, they give you a username and password, and they're saying, I claim to be this username. I claim to be the owner of this account. Here's my password, and if the password is the same as the password for registration, you're in. If not, you're not. I don't think I have to go too far into that. And with registration, it's common to have extra information. One of those pieces of information is email address. We can have email verification is what a lot of sites do. As a user of the internet, we see this all the time. You create an account, they send you an email, you confirm that email, and then they let you in. The reason for this is to combat bots, is the primary reason for this. Bots can generate thousands, millions of accounts very quickly with a simple script, but if they need a valid, legitimate email account for every single one of those bot accounts, that's a pretty big hurdle for them to handle. It gets a lot tougher to run these bot farms that create a bunch of accounts because they're not going to be able to verify that many email addresses. So that's why we always have to, one of the reasons why we always have to verify our email address before we can really interact with a site. So there's sometimes more to the process. For our purposes in this course, for our purposes in this course, username and password, and we're good with that. And that's about it. I don't have much to say about authentication mechanically. From the user perspective, you can see what authentication is. You register a username and password, you log in with username and password. If you type your password wrong, you're not authenticated, and then you can't log in. I don't think I have to spend too much time talking about that. We have the mechanics of exactly how we do that in this class, which is a registration form, a login form. It's going to take username and password and URL encode it as the body of a post request. So the mechanics, not much to say about that either. We've talked about how that works. I showed you the structure of query strings, which is the URL safe, the percent encoding. Talked about forms with a post request that'll take the query string and put it in the body of the request. So not really much to talk about. That's authentication, baby. What more do you want to know? Ask me questions if you want to know more. I'll talk about it. The rest is what happens behind the scenes. And the biggest thing we have to talk about with this is how to store those passwords. So we're not just going to store the passwords and check if the passwords match based on strings. It's not how we do things. And the problem with this is that the server is implied, to get this functionality to work, it's implied that there will be a database. You're going to be storing username and password in a database somewhere, and that database becomes a very lucrative target for attackers. So if you're open to any SQL injection attacks, for example, or usually social engineering attacks, to be honest, but if you're open to any attacks that compromise the database, if an attacker compromises the database and you're storing username and password, they have everybody's login credentials. They can log in as any user of your app, which is, I shouldn't have to say, very bad. It's a very, 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 very bad thing. So we have an extra security concern once we're handling user passwords, and we have to be responsible with the way we do this, the way we handle these passwords. What we won't do is store them in plain text. Never, ever, ever store your passwords in plain text. This is terrible to do. Do not store passwords in plain text. This is such an important thing. It's basically achieved meme status in software engineering. Don't store your passwords in plain text. Don't do it. Don't do it. So we want a different level of security. So I mentioned attackers, but what we want is a level of security with our passwords that anybody with access to the database can't know what your password is. We would like it so that even the admins, even the DevOps team, the sysadmin, the CEO probably won't even have access to the database anyway. Don't give the CEO access to your databases. But depending on the company, I guess. But they shouldn't even have access to your passwords. They can read the database, but we want it so they can read your database, and the database functions the way it's supposed to. If you log in with the right password, it still logs you in, but that nobody can see what that password is. And we're going to do that by hashing and eventually salting as well. We're going to store salted hashes of our passwords in our database. That's how we're going to solve this problem. But let's talk about what that even means. It means we're going to use a hash function. And a hash function is basically a function with special properties. That's about it. So a hash function is going to take in any input and return some output with some properties to it, usually fixed length. And you've seen these before. You've seen them at least in CSE 250, where you used hash functions to build hash tables. And that property you wanted was, here's an input, give me a value from 0 to my number of buckets minus 1. So I can use that as an index to insert into my hash table. That's a hash function, but hash functions do not have any security properties to them inherently. Do not use, when I say store hashes of your passwords, don't just store your passwords. Do not just pull out any random hash function, say here's a hash function, hash my password, store the hash, I am now secure. Do not do that. If you use the hash function you used for hash tables in 250 as your hash function for passwords, you are not adding any security to your app. I shouldn't say any, but you're negligible security. Actually, probably worse than storing plain text passwords, depending on your hash table configuration. Probably even worse than just storing strings. Because I'll expand on that a little bit. Because you'd have tons of hash collisions with passwords. You wouldn't even have to guess the right password. You just need a password that collides with the hash of the correct password. And if your hash function doesn't have, the output space is pretty small, random guessing is going to get you in quite often. So hash functions, not necessarily secure, but we want our cryptographic hash functions. It's a subtle difference, but enough that I want to make sure I make this point. We need a cryptographic hash function, which is a hash function that's made for its cryptographic properties. Namely, it's made to be a one-way function. If I take this string password and take the SHA-256 hash of it, which is the hash algorithm I'll pick on for this lecture, this is the SHA-256 hash of that value. And the SHA-256 has the property of a one-way function where, given the hash, you can't compute the inverse of that to compute the plain text that generated it. This is what we want from our hash functions. And I say that kind of strongly, a little too strongly. What I mean by that is there's no publicly known method for reversing a SHA-256 hash. I always have to qualify this because there's possibly some attacker, some villain, I guess. I don't know. I want to say hacker, but I got to stop overusing. Supervillain? Yeah, some supervillain out there who has a way of reversing these hashes, taking the inverse of a SHA-256 hash, and just isn't going to tell anybody. Because why would a supervillain tell everybody their secrets? Like, hey, this is how I'm hacking. They're not going to say anything. So there's no publicly known available way to reverse these hashes. I can say that much. And sometime in the future, there might be some researcher might find that way and release it to everybody, and then we'll just move on to the next hash function. SHA-3 already exists. We can move on to the next one. And I already have this open in my browser, so I'll leave it at that. So we'll pick on SHA-256. This is a cryptographic hash function. And moving forward, I know I made this nuanced point and everything, but moving forward, when I say hash function, I just mean cryptographic hash function moving forward. I just don't feel like saying that many syllables. But the point of storing hashes of passwords, make sure you're using a cryptographic hash function. Don't just pull out any old hash function. Don't use... I'll still use this as an example, but don't use MD5, for example. It is a hash function. It is a cryptographic hash function. But there are known attacks for MD5, and this happens in cycles. There are known attacks that are exposed, and then we stop using those hash functions for cryptographic purposes. We still use that for file integrity purposes, for what it's worth, but don't use a compromised cryptographic hash function or a non-cryptographic hash function. So, again, not enough to just store hashes. They need to be secure hashes. Okay, so SHA-256... how it works is with a lot of bit-level operations. Takes the input, basically scrambles, for the very high-level overview, basically scrambles the bytes at the bit level with these bitwise operators and spits out a hash on the other side. The point I want to highlight on this slide, the reason I'm saying this at all, is that it's very fast. Bitwise operations are extremely fast. They're usually a part of the processor's instruction set, one clock cycle to compute each one of these operations, extremely fast, as opposed to more mathematically intense computations, like even a multiplication. A multiplication is a very complex operation. I mean, not terribly complex, but much, much more complex than something that maps directly to the instruction set over one clock cycle. Very, very, very fast to compute these hash functions that are bitwise, working at the bit level. Okay, so we're going to store hashes of our passwords, and we're done. Problem solved, right? Now, with these cryptographic hash functions, we got the property we want, that even the admins of the site cannot recover our passwords. They see the hash. They can't compute the plain text that generated that hash, so they can't compute your password. So we are done. Secure. We can all take a break, breathe easy, knowing our passwords will never be compromised. Of course, that's incorrect, or else this would be a much shorter lecture. That's absolutely incorrect. This is a surprisingly, upsettingly common misconception. Just because you're storing a hash of something does not make it secure. It does not make it secure. This is a misconception I've even seen in peer-reviewed work, and then my work would be compared to their work, and they'd say, those guys over there, they're super secure. Look at them go. And I'm like, well, no, they just said, don't worry, bro, we hashed it. and called it a day. And they were completely wide open to vulnerabilities, to attacks and everything. I'm like, look, I'm trying to build something actually secure here. Stop comparing me to them. But so it's a pet peeve of mine for personal reasons, but also very common misconception at all levels. Very scary that this misconception is out there. This is vulnerable to the simplest attack imaginable, a brute force attack. What a brute force attack does is say, okay, I can't compute the input given a hash, given the output. I can't compute the input, but you know what I can do is just guess a whole mess of inputs. If I guess an input, I have a guess. I think your password might be this. Hash it, and then check if the hashes match. If the hashes match, I just guessed your password. So we're not computing the input based on the output, but we are using the hash function for its intended purpose of take a guess, hash it, and check if the hashes match. And what was that hash function? Ridiculously fast. It's built to be fast. So I can launch a lot of guesses and just brute force the password by guessing every possible password you might have ever thought up until I have one where the hash matches your hash that is stored in the database. This is a brute force attack. Just guess a whole bunch, use the one-way function in the one way that it was designed to run in, and just take a bunch of guesses. Very effective. It works. If you're, say you're hashing, and I've seen this, it's scary, but you have one bit of information. It's like a yes-no question, and you're storing the person's answer in the database. But you hash it, so it's secure, right? Well, no, there's only two possible hashes. It's either yes or no. I'm just going to hash yes, hash no. It's one of those two. Okay, so let's take a look at this in action. I want to show a few things first. Let's get rid of that. And the first thing I'm doing here, I have a little bit of Python code to play around with hash functions. First, I'm just going to hash a value. Let's change this. I used pass in the last one. I want to use something that's 4 characters. That's why nobody's in chat. I'm in the wrong channel. I'm in the wrong app. I was in Element. You're storing an int anyway. Why not use all the space? Why do math instead of using a constant? Oh, that's in reply to someone. It's in the last lecture too. I'm just all lost now. So it means that we should let the user use a SHA-256 hash on the client and then use a post request and send it to the server. No. For reasons. I'm glad you asked this. I don't know how deep I want to get into this right now because when we talk about encryption, I will talk about this exact question. Why not hash client side? I want to finish talking about what hashing even is first, but I'll give a brief answer to this. Why not hash client side? It's because the hash is effectively their password now. And that password has as much entropy as whatever they typed in before generating the hash, whatever it's a hash of. So you don't actually gain anything by hashing before the client sends the password to the server. And you can test this. I'll demo this in lecture later, but if you want to play around with it right now, go to, any site ever that has login. Anyone that you choose. Open up your browser console, open the network tab, go to the login form and type in your credentials, or any credentials. It doesn't have to be your credentials, but type in the form and click login and look at the request that's sent. It will send your password in plain text. 100%, I shouldn't say 100% of the time. 99.99% of the time. I did find one portion of one app. It had to be the mobile version of their, anyway, I found one in all my time trying this. They're sending your password in plain text. One time they were using MD5 hash and sending that, but only the mobile version of their web app. It was weird when I finally found that one. So now I can't say 100%, but try it. They're sending your password in plain text. Nobody's doing that because it doesn't help. Client-side hashing doesn't help. It doesn't do anything. It doesn't accomplish anything. Because you'd think it would, but I'm not creative, so I'm just going to use the second half of password and do word. When I hash with SHA-256, the word word, I get this as the hash value. That's what I'm printing as the hash digest there. Right, this is my hash of word. And when I go to the browser, I'm going to go to this site that I linked in the slides. I'm going to type word, hash it. I think this automatically copies that to my clipboard, but just in case. And I'm going to paste that hash, and they are identical. SHA-256 is an algorithm that's completely independent of implementations of the algorithm. So on the website, it's computing SHA-256 hash, probably with JavaScript. I assume it's not hitting a back-end server or anything. And my Python library here, they computed the same exact hash. The algorithm is the algorithm, no matter who's implementing it. If it's implemented properly, it's going to give you the same exact output on a particular input. So when an attacker compromises a database, has a hash of your password, they can go offline into their lab and perform their brute force attack with their implementation of the algorithm and be able to crack this thing. And if we take this hash, and I'm going to run it through my code here, which is going to launch a brute force attack on one of these three libraries. I'm going to start with lowercase letters. I just chose lowercase letters for this. And it's just going to try every single guess until the hashes match. And it cracked that password almost immediately. We go back, and now, just as a proof of concept, I have no creativity in lecture. I looked at my phone and thought phone. But I got too much running through my mind to be creative, too. So here's the hash of phone. That word did not hit my Python code at all, because word, maybe I just did something where I stored that variable or something. I'm going to paste it here. I'm going to run my brute force algorithm. And it's just, as is implied here, tries every combination of those characters of length 1, length 2, length 3, length 4, length 5, and spits out what the original plain text was by just giving it the hash. And there's something we're going to do later. By the end of the lecture today, we're going to add salts to the end of our hashes, and we'll build up to it. I'll explain why and everything. But we're going to end up adding a bunch of random stuff to the end of our string. And this salt is going to be appended to our password before we hash. And the salt is going to also be stored in the database along with the hash. So the attacker is going to know what the salt is. And my claim is that so I can tell my attacker that in my attack code. And they're going to know the hash. And when we do add the salt, that's not going to make anything more secure. I'll give it the new hash. I'll run this. It's actually not going to make things more, well, it will make things more secure. There's a reason why we do it. But it will have the same effect on my brute force attack. A brute force attack doesn't care that salt is there. It's still going to crack that password. So we don't add what we call entropy to the password by adding the salt. So I'm doing that ahead of time just because I have the code open. I want to do that now. But common misconception, adding a salt does not make the password any stronger at all. Okay. So with a brute force attack, the attacker is going to get your password. So we went from, okay, we'll just store a hash of this password and we're good, to, holy crap, even hashes of the password are not secure. Why the hell are we even doing this? Like, why even hash if they're just going to launch an attack and crack my password anyway? The answer is entropy. I already introduced this word just a few seconds ago, but entropy is going to be the answer. Entropy is a measure of how many guesses an attacker with running a brute force attack would have to guess before being guaranteed to guess your password. So it's a measure of how many guesses they need to guess, which correlates to how long it's going to take them to crack a password. Hashing and salting the request prevent man-in-the-middle attacks. Never mind, you answered my question. We prevent man-in-the... I did answer your question that no, it wouldn't. But we do prevent man-in-the-middle attacks with encryption and certificates. That's why you need certificates on websites you visit. That's specifically preventing man-in-the-middle attacks. Because even with encrypted traffic, without a cert, do supercalifragilisticexpialidocious. My brute force algorithm will not get there. It will never get there. Why is salt stored in the database at all? If it wasn't stored in the database, your user would have to remember it and type it when they log in. Salted hash browns. Not hungry. I want to eat. All right, so entropy. We usually measure this as log base 2 of the number of guesses because the numbers start getting too big to reasonably talk about. And bits of entropy logarithm growing so slow, it keeps the numbers nice and small. And usually 80 bits of entropy is our rule of thumb to consider ourselves secure. And running some numbers, if we have just lowercase letters, like I did in the guesses that the passwords that we just demoed, only lowercase letters, and I have 2 purely random lowercase letters, I have 676 bit entropy, total guesses that would have to be guessed, which is about 0 entropy, no entropy at all. If I add uppercase letters in the mix, I have an alphabet of size 52, and I get up to 2704 guesses, which is roughly 0. That's going to take the algorithm no time at all. You can see how fast my algorithm goes through guesses of 1, 2, and 3. It's not till it gets to 4 that it even slows down at all. So, can entropy save us? Because my brute force attack, which is, you can see it's less than 100 lines of code, and a lot of the code isn't even doing much. The algorithm itself is 20 lines. To do that, it's not complex, it's not even optimized or anything, and it's still breaking hashes pretty quick if they have low enough entropy. Let's talk about entropy. Oops. So I have some more code here. What this is going to do is take an alphabet size and a password length, and the number of attempts per second that an attacker can execute. And I want this set to 1 million. Do I have it? 1 million. So 26, length 4, actually correct length 5 password in some number of seconds there. Let's run this. I do need this open. Let's run this and see how long it would take an attacker to crack this password. And I'm guessing my algorithm does about 1 million seconds. I should probably run that sometime and crunch the numbers, which is this many total guesses, about 11 million total guesses, or 23.5 bits of entropy. And with 1 million guesses per second, it's going to take about 11 seconds. That feels about right for my algorithm. This is probably about 1 million guesses per second. 1 million's a small number to a computer, especially when SHA-256 runs pretty quick. I can have a pretty inefficient algorithm. Again, I didn't optimize anything here. I just wrote the first approach that I thought of. Not optimized, and still getting 1 million guesses per second. So my algorithm's going to crack that pretty quick. What happens if I increase the length? Let's go to 8. Again, just using lowercase letters. And now my same algorithm's going to take days to crack that thing. Just lowercase letters only and a password of length 8, strictly, purely random characters from that alphabet. This is why we have tougher password criteria. 8 characters, uppercase, lowercase, number, special character. We're trying to get the alphabet size up to 90, about 90 with that, and require length 8. This is a general criteria. Again, this is assuming if somebody's coming up with purely random passwords, which nobody does, but purely random passwords out of 90 characters and a password of length 8, my algorithm doesn't do so well anymore. It's never going to finish within my lifetime. We're not going to finish. That's a lot of guesses that needs to be taken, and you can start seeing why we use bits of entropy. This number, I don't even feel like figuring out what number that even is, but it's about 52 bits of entropy, and 52 is a number I can wrap my head around. But this isn't what attackers are going to do. This is just running on my laptop, single-threaded, non-optimized code. Attackers aren't going to do that. They're gonna use powerful GPUs, possibly botnets running guesses on this hash. They like to use hardware, like a flash drive that computes the hashes for them, so it goes faster. It kind of goes hand in hand with Bitcoin mining or crypto mining at all. The crypto mining found out faster and faster ways to compute hashes, and the attackers can use, if it's the same hashing algorithm, can use it for cracking passwords. Anyway, 1 million is more like a trillion. Is a fairly reasonable amount of guesses per second. Maybe a little generous, but a fairly reasonable, not outrageous number of guesses per second for an attacker to have. And now all of a sudden it's taken a little more than an hour to crack your password. And I'm going to be even a little more generous. I'm going to give them 100 trillion guesses per second. 100 trillion guesses per second, less than a minute to crack that password of 8 characters, uppercase, lowercase, special numbers. 100% purely randomly generated password. It's going to be cracked in less than a minute to this admittedly generous number that we're giving the attacker. But as computing hardware and software keeps getting better and better, in my opinion, hardware is getting better and software is getting crappier. But but that's still within the realm of possibility that an attacker can launch 100 trillion guesses per second. So let's start increasing the password length here. Let's go to 9, and we're getting up to 58 bits of entropy, and it's already taken them an hour, even with that generous amount of attempts we're giving them. So let's keep going. 10, 65. We're not quite at that magic 80 number yet, but it's starting to slow down this algorithm. Even that super powerful super villain attacker is taking 4 days to crack one password. So we're starting to slow them down just by increasing our password length a little bit, just a little bit. Now let's skip over 11 and go right to 12. We have a password length 12, purely random from all the characters available to us. They're not cracking that anymore. 100 trillion guesses per second, they're still stuck. They're still not cracking your password. And we're not quite at the 80-bit, the magic number, so let's just crank this all the way up to 15. Now we're past the 80-bit mark, and it's going to take them quite a while to crack this password. This is the power of exponentiation. This is why we love exponents in computer science. Of just going from 8 to 15, let's go to 16 and just double the length of this. We'll just double the length of the password, and it goes from being cracked in less than a minute to taking that long, millions of years, 100 million years, something, I don't know, a big number. And then if you're using, and I recommend using a password manager, and you just crank that thing up to, say, 20, and say, generate me a random password, strictly random password of length 20. They're not cracking that password. At 130 bits of entropy, the sun will burn out before they crack your password. At 8, they were cracking it in less than a minute. Exponentiation is a very, very powerful thing. Unless your algorithms have exponential runtime, then your algorithms don't run. Even on an input of size 20, they'll never finish. So use a password manager. Very, very quickly, very fast that the number of guesses grows. Okay. Oops, wrong way. So entropy does save us. How quickly those numbers go up is very, very important. So with weak passwords, even if you're following the criteria, length 8 and everything, purely random, which nobody's going to do, your password is not very strong at all to a sophisticated attacker. Granted, 100 trillion guesses per second, yeah, that's a very powerful attacker. They really have to want your password. They really have to want to go after you to dedicate those resources to it. But if they do want to, they're going to get your password. So just crank up the length, and that's fine. But that's not what humans do. That's not what we do. Again, unless you have a password manager, that's not what you're going to do. You're going to come up with a password that you can remember. You're not going to come up with a purely random password. So when we have passwords, length 8, one of these, one of those, the whole thing, that's become pretty standard these days. If your users are just meeting the bare minimum requirements, they're going to come up with some common password. They're going to come up with like the string password. They're going to capitalize the P. They're going to change the A to an @ sign, the O to the number 0, and then they're going to meet your password criteria, and they're going to say, I got a strong password now because the thing said strong on the web app. But now even a purely random password didn't really have enough entropy. The passwords people actually come up with have basically no entropy. Once they launch a dictionary attack, the attacker starts with a list of common passwords, which are published out there. They're out there on the internet. And then start using these common substitutions for all the guesses. They're going to get these passwords much, much quicker than they should because we like to remember our passwords. So we don't have purely random passwords unless you have a password generator. Like writing mine down. I mean, that gets a lot of hate, writing your passwords down, but like somebody has to have physical access to your space, so you have to trust the people around you. But if you write down password hints, then they can't get it either. But we're worried about the invisible attackers out there on the internet that we can't see. Sponsored by Bitwarden, which is the one I use. Okay. That's what I was saying. So it's a battle with your users. It's hard to have more criteria. Some sites will try to enhance those criteria, say you have to have a password of length 10 or so, and you lose users doing that. Like some users don't want to do that. I've been to a site where even I said, your password criteria are too much. I didn't really want to use this app anyway. I was just kind of checking it out. I'm out of here. And I didn't use the app because they wanted me to be secure. These days I use a password manager. I would just click generate password, whatever. But it's a battle between devs and their users. The users want to do everything they can to be insecure. And how much do we do to keep them secure? Even when that security could drive them away, it's a tough one. It's a tough question. And I was going to say for better or worse, but for worse, the common criteria have the ones that I even put it in the homework as the criteria. Those ones kind of stuck, and it's not secure enough. But anyway, okay. So we're going to come up with strong passwords, and then we're good, right? Well, not quite yet. Rainbow tables are very, very scary attacks. So we talked about brute force, which is just the dumbest attack that anybody can launch, even me in 20 lines of code. Dictionary attacks, which are a little more sophisticated, but not much. They're not getting too crazy with it. And then rainbow tables, the third and last one we'll talk about, is a lot scarier. These things are extremely powerful. Luckily, we have a very, very simple, clean solution that makes these completely irrelevant these days, which is called salting. So foreshadow, this is what we're using salting for. But rainbow tables, the way these work is instead of compromising a database, getting the hashes, and then attacking a hash and trying to crack that hash, what rainbow tables do is pre-compute a ton and tons and tons of guesses for the hashes that you're going to crack in the future. So we're going to pre-compute. The attacker's going to pre-compute. What they do is take a guess. This is my guess for the password. They take that guess and they hash it, and then they apply a function to that hash to generate the next guess in this, what they call a chain. So we have a function that we apply to the hash because the hashes are these big, long, random strings that nobody's going to use for their password. So we have some function that will turn that into something that's a viable guess that somebody might actually use for their password again. And then they hash that, and then apply the function to come up with their next guess, hash that, and then keep going until they build this chain of millions, billions, trillions, however long they want these chains to be, of password guesses that they encode in this chain. And then to store a chain, they're going to store two values, the first guess and the last hash. Those are the only two things they store to represent that entire chain of potentially trillions of guesses. And then they'll come up with millions, billions, trillions of chains and store all of these chains. And the parameters, they can adjust these parameters depending on how much storage they have for the rainbow table, how much time they have to pre-compute the things. If they have teams of people pre-computing the same table, whatever, they're going to adjust those parameters of how long the chains are and how many chains to store. Now they want to crack a hash. They finally got into a database, or maybe they just got a single hash, something, they got a hash that they want to crack. What they're going to do is take the hash that they want to crack, apply their function to turn it into a guess, hash that, apply the function to turn it into a guess, do the same exact thing they did to generate the chain until they have a hash that matches the end point of any of the chains they have stored. Once they have that, they know which chain contains the password. They go to the beginning of that chain, which is the only other value they stored for that chain. They go to the beginning of that chain and run through the process again until they have a hash that matches the hash they're cracking. And they back up one step. That's the plain text password, or at least a plain text that maps to the same, that has a hash collision with the password. And then they had the password, they typed that in, boom, hacked into the account. Yeah. I don't remember off the top of my head how Alan Turing cracked the Enigma code. Is that what you said? I don't remember the exact details of how we broke it, so I can't give you a solid answer, but I'll say maybe. I just don't remember all the details off the top of my head. It's not coming to me right now, but it might be similar. So these things are very scary. It makes it very, very fast to crack hashes because of all the pre-computation that they get to do. We completely neutralize these things with salting. So what salting is when we get a password, instead of hashing it and storing the hash, that's what we used to do as of a few minutes ago. For like 20 minutes, that's how we stored hashes. Instead, we get an account registration. We have username and password. We're going to generate a random value, a very long, ideally high entropy random value, append that to the end of the password, and hash that concatenated value. We store that as the hash, and then also store the salt. Then when somebody wants to log in, we say, okay, who are you claiming to be? Pull their record, which has the hash and the salt. Take the salt, append it to the end of the password that they're using as their login password, hash that, and check if the hashes match. And if the hashes match, then it's authentication as usual. So the salt has to be stored in plain text because the user's not going to remember what the salt is, and we need the salt during login, during authentication. So we need to have access to that salt, which means the attacker also has access to the salt. So it doesn't add any entropy to the password itself, but what it does do is renders these rainbow tables completely useless because all of those guesses that they had, the vast, vast, vast majority of them will not end in that salt. Probably zero of them. We're probably, statistically speaking, a huge, huge rainbow table isn't going to have any matches for that specific salt. If you have, like, say, over 80 bits of entropy, if you're over our rule of thumb, none of the guesses are going to end in that salt. So they're completely useless. You could build a rainbow table for a specific salt, and your function that takes a hash and generates the next guess, you make sure that ends with the salt, just append it, Then you could build a rainbow table for a specific salt, but at that point, well, you have to compromise the database, get the hash, get the salt, then build the rainbow table. It defeats the whole purpose of pre-computing. You can't pre-compute when you don't know what the salt of the hash is that you're trying to crack. So completely useless. All these hash tables that are out there, useless. Unless you forget to salt your hashes, then some attacker, if they do get access to your database, they're going to say, wait, these things aren't even salted. They're going to pull their rainbow tables out of the trash and crack all your hashes. So make sure you salt your passwords. This is why we salt, to prevent rainbow table attacks, even though the salting does not do anything to brute force attacks, dictionary attacks, or any other brute force style attack. It's not going to do anything to those attacks, but it will render rainbow tables useless, which was the scariest threat. So it's good that we can get rid of those with a pretty clean, elegant solution. So when a user registers, we take their, I just ran through this, didn't I? We generate the salt. I just ran through this. I'm not going to do it again. To do this in practice, in the real world and on your homework, we're going to use the bcrypt library. I haven't had anyone try to homebrew their things, so I say recommended, but you just use the bcrypt library. Everything we talked about, I don't want you homebrewing your own authentication, all your crypto stuff, because it's easy to introduce security risks that way. It's not something, even in a course where I say we're building everything from the ground up, even in that context, I don't want you building your hash algorithms and salting algorithms. I don't want you building those from the ground up. Don't get in that habit, because there will be vulnerabilities. Use a library that is in the cat and mouse game with the attackers and has the top of the line, state of the art countermeasures built into it. Bcrypt will do everything we talked about today, everything you needed to do in 3 methods. And when you hash a password, you generate a salt and hash a password with bcrypt, it will store the hash and the salt in one single value. So there's only one thing to store in your database. And you pull that one value, ask bcrypt to check the password against that value. It will extract the salt out of it, append the salt, hash it, check against the hash. It'll do all the minutia for you, all the little steps. Make sure you're using bcrypt and storing these bcrypt salted hashes in your database. And redirects. This is the first time we'll need redirects. I don't really have a better place for these slides, so I just tack it on to the end of this one. We'll do this in like 2 minutes. If you want to redirect the user to a different page, we're going to respond with a 300-level response code, and that's going to tell the browser to send the user to another page. For this example, I'm using 301 move permanently. 302 is the one for the homework. 302 found is going to be a temporary redirect, which is going to avoid the browser from caching the redirect and prevent the browser from skipping the first request, which is going to be registration and login. We don't want users skipping those. When you send a redirect, use the location header to tell the browser where to redirect the user to. And these can be relative or absolute. So this is a relative path. If you just specify a path, it's going to use the same protocol, host, and port as the original request. So a user visits old path, I respond with this, then the browser is going to send another request to new path, and whatever new path returns, that's what's rendered to the user. So new path should be returning some HTML, ideally. This can be absolute. So if I want to send them off-site, I start with the protocol, put the full URL there.